The first calculation that needs to be addressed in the vapor pressure lab is correcting the measured volume of the bubble. Normally, in a graduated cylinder, when it's right side up, we measure volume by taking a look at the meniscus. The meniscus is the little curvature of a liquid that will appear in the log, and it's called the meniscus, and we measure looking at the bottom of that curve. Because our graduated cylinder was turned upside down when we were collecting our data, what happens is the meniscus ends up being backwards, and we have to correct our measured volume. The correction for this is to take your measured volume and subtract from it 0.2 milliliters, and that will give you a corrected value to account for the upside down meniscus. So what we would need to do is take the observed volume of the bubble. In this circumstance, let's say we observed a bubble of 4.4 milliliters, subtract from it a correction of 0.2 milliliters to account for the upside down meniscus to give us our corrected value for the volume of 4.2 milliliters. It's the corrected value of the volume that we would now use for subsequent calculations. We also have to switch the milliliters to liters, since liters is the unit of measure that's used later in the PV equals nRT calculations. Shifting the decimal 3 places to the left will convert our volume to 0.0042 liters, and that's the value we would now use in calculations for the lab exercise. Correcting the volume by subtracting 0.2 milliliters needs to be done for each bubble volume reading in the lab, and then convert each volume reading to liters so it's ready to be used for the PV equals nRT calculations. The next lab calculation involves using the air pressure in the room, the temperature of the bubble, and the corrected measure volumes to find the moles of air that are inside the bubble trapped in the graduated cylinder. A key concept here is because the bubble is flexible, meaning that it has a volume that can change, the bubble pressure will always be equal to whatever the pressure in the room is that's pushing down on top of the water in the beaker. The pressure in the room will push on the water pushes on the bubble, and the bubble will adjust itself's volume so that the pressure in the bubble is always the same as the pressure in the room. Another concept for this part of the lab is that the moles of air that are trapped inside the bubble, inside the graduated cylinder, remains constant throughout the lab exercise. Once the graduated cylinder is turned upside down, it's no longer possible for air in the room to make its way into the graduated cylinder and change the number of moles of air that are inside that bubble. Consequently, the moles of air that are trapped inside the bubble remains the same from beginning to end of the lab exercise. Now, in the lab exercise, the reason we cooled the bubble down to 5 degrees, getting near zero, is that as we get cooler and cooler, more of the water vapor that's in the bubble turns back into liquid water. At 5 degrees Celsius, we can make an approximation and say that at this temperature, essentially all the water vapor is now out of the bubble, and the only gaseous particles remaining in the bubble at 5 degrees Celsius would be the air from the room that was trapped inside that bubble. So what we can do, we'll start out our first calculation. We want to make sure we calculate the moles of air trapped in the bubble at the lowest recorded temperature, which for many of you will be near 5 degrees Celsius. In our sample set of data for this example video clip, at 5 degrees Celsius, our volume is 0.0042 liters. We can use this in PV equals nRT, rearranging to solve for the number of moles. Now, when we set up the calculation for PV over RT to give us the moles of air in the bubble, one thing we have to consider is that the pressure inside the bubble is the same as whatever the pressure in the room is that's pushing down on top of the water. Just as an example, typically in Darien, Illinois, air pressure is in the area of 1 atmosphere. That's why our pressure value in this problem is 1 atmosphere. We use our volume at 5 degrees Celsius, the value for R, convert our Celsius to Kelvin, and this will allow us to calculate the moles of air that are trapped inside the bubble. In our sample calculation, the number of moles of air that are trapped inside this bubble at 5 degrees Celsius is 1.84 times 10 to the negative fourth moles of air. This value will now remain constant for all remaining calculations done in the lab. The reason it stays constant is, once again, air cannot get into the bubble when the graduated cylinder is upside down. The amount of air that's originally trapped in the bubble remains constant throughout this lab exercise. We calculated the air at 5 degrees because at 5 degrees there's no water vapor in the bubble, it's only air. The next calculation that we'll do for the lab is to now calculate the partial pressure of air in the bubble. Now, as we increase temperature to 50 degrees, 55 degrees, 60 degrees, what's occurring is at a higher and higher temperature, more and more of the liquid water becomes gaseous water to be trapped inside the bubble, causing the amount of moles in the bubble to increase, because now there will be moles of air in the bubble and moles of water vapor in the bubble. However, the total pressure of the bubble will remain equal to the pressure in the room because the volume of the bubble is flexible. The volume can adjust to accommodate the additional moles of water vapor, keeping the total pressure in the bubble always the same as the pressure in the room. However, at this point we'll calculate the pressure of just the air in the bubble at each temperature, because we now know that the moles of air inside the bubble is 1.840 times 10 to the minus 4 regardless of the temperature. This is our moles of air, and this remains constant again throughout the lab exercise. Now, doing some sample calculations with the sample set of data, the pressure of air in the bubble at 50 degrees can be determined, and also at 55 degrees. The key thing here is that if you'll notice, the moles of air trapped inside the bubble is staying the same in both calculations because the moles of air in the bubble again remains constant. What we've changed in each calculation is the temperature and then the volume of the bubble that was observed at each temperature. With our sample set of data, at 50 degrees, the pressure of air in the bubble comes out to be 0.787 atmospheres. As we increase the temperature, the amount of water vapor in the bubble is going up. The bubble enlarges to accommodate the additional moles of water vapor present. Total pressure of the bubble remains equal to the outside room pressure. So we observe that as the temperature increases, the partial pressure of the air starts to diminish. Our next calculation is now to calculate the pressure of the water vapor that's trapped inside the bubble at each temperature. A key part to this calculation is recognizing that the pressure in the room is always equal to the total pressure that's inside the bubble. The total pressure inside the bubble is a combination of the water vapor that's present at temperatures above 5 degrees Celsius and then the pressure of the air that's also in the bubble, which we just determined in calculation number 3. We can rearrange this relationship that the total pressure in the room is the water vapor pressure in the bubble plus the pressure of the air in the bubble to get an equation where the pressure of the water vapor in the bubble is equal to the pressure in the room minus the pressure of the air that's present in the bubble. If we now continue with these calculations, we can once again use that the pressure in the room in Darien, Illinois is roughly 1 atmosphere. We can subtract from that the pressure of air in the bubble that we determined in the last calculation, and this will allow us to determine the pressure of water in the bubble. This first one is at 50 degrees Celsius, and the second one is at 55 degrees Celsius. Now, one thing that we can notice here comparing the 50 degrees Celsius to 55 degrees Celsius is that as the temperature goes up, the pressure of the water vapor in the bubble is increasing, which we would expect. This is the vapor pressure of the water that's in that bubble, and with any liquid, as the temperature goes up, we'd expect the vapor pressure to go up because at a higher temperature, more of the liquid particles, this case being water, can become gaseous. With more gaseous particles, the pressure we'd measure would go up, so the vapor pressure of the water at a higher temperature we will see getting higher and higher and higher. The next step in the calculations to prepare to make our graph is to now take the water vapor pressure that we found at each temperature and find the natural logarithm of each of these water vapor pressures. This involves just taking the water vapor pressure we found at each temperature and taking the natural log of that to find out what this value is, and this will be used when we create our graph, and the graph is used to find the heat of vaporization for turning liquid water to a gas. The next calculation in our process involves finding 1 over the temperature for each temperature in the lab using the Kelvin scale. Key thing with this is to use Data Studio to create the graph. 1 over the temperature needs to be displayed as a decimal so you can enter this. Keep your decimals, go out to 6 places past the decimal so that the numbers for each 1 over temperature value actually give a different value when you enter them into Data Studio. So carry this out to 6 places past the decimal, expressing your 1 over temperature in decimal form. The next part in the calculations involves using your natural log of the vapor pressure of water, which we found, and your 1 over temperature values to make a graph. Now the axes of the graph are selected. We'll make natural log of the vapor pressure of water the y-axis, and we'll make 1 over temperature the x-axis. The reason for this selection is that by making the natural log of P the y-axis and making 1 over temperature the x-axis, the slope of the graph will allow us to determine the heat of vaporization for water. By making natural log of the vapor pressure, again the y-axis, the x-axis 1 over temperature, then our expression y equals mx plus b, if we match it up with the Clausius-Clapeyron equation for figuring heat of vaporization of a liquid, we get that the slope is equal to the negative delta HVAP over R. Rearranging this, we now get that negative R times the slope will give us the heat of vaporization of our liquid. With the sample set of data that we've generated in this example calculation for the video clip, the slope of our data that we have comes out to be negative 4,266. This can be readily put into the equation of negative R times M to give us the heat of vaporization of water. A key thing here is that the R value, which is the gas constant, because this is an energy calculation, the R value needs to use units that include joules, which is a measure of energy, so the value for R is 8.31 joules per Kelvin mole. So to use the graph to get our calculation, we put in negative R, negative 8.31, and then multiply it by the slope we got from our graph, the negative 4,266, and that will give us our heat of vaporization, or the amount of energy required to turn liquid water into gaseous water. This gives us an experimental value collected from our data of 35,450 joules per mole for the heat of vaporization of water. The known value for water is 42,700 joules per mole, which can now be used to do a percent error calculation for the results we got in the lab exercise.